skills that are necessary for CAD. Then we're going to go to Excel. We're going to look at statistics. We're going to specifically talk about rate of change, which is a huge part of engineering, which you've talked about already in physics and in math. And then we're going to talk about instrumentation, the last bullet there. And that has to do with calibration using certain tools. So we'll talk about that at the end of this chapter. General stuff. We're going to talk about circles and general polygons. So diameter, radius, circumference, area. These terms, they need to be familiar by now, right? I'm going to quickly outline what they are and how they can be useful in engineering applications. So first, let's take a look. We just draw a simple circle. Okay, our diameter we know is the distance across the circle. Let's say there's the center of the circle. This is our diameter right here. The radius is the distance from the center of the circle outward. Okay, there's a radius. If those terms are not memorized, you're going to not know what to do in this class. Okay, these are things that you need to know. So radius is half the diameter. Circumference. We're going to need circumference for CAD applications. We need to know how to calculate and determine circumference for certain things. Circumference equals, there it is, also known as pi d. Okay, either way works. Either way works. It depends on if you're given an application where you know something about the radius or if you know something about the diameter. Depending on which one you use, you can utilize the formula. Area, pi r squared, or in terms of diameter, anybody know that one? Think about it. You'd replace r with d over 2, and then you'd have to square that whole thing. Replace r with d over 2, but then you have to square d over 2. What does it become? There it is, pi d squared over 4. Okay, because you're going to put d over 2 in for r right here, and then when you square d, it's d squared, and you square the 2 in the denominator, it becomes a 4. Either formula works. Okay, either one works. Good so far? Yeah. Okay. Now, there's a term that we should utilize this year, which is called hydraulic diameter. Write it down. H-Y-D-R-A-U-L-I-C. Hydraulic diameter. The importance of this term is for when you're using cross-sections that are not circles. You could have a square or rectangular HVAC system, like the heating ducts that go into the ceiling. They're usually rectangular cross-section, they're not circular. But when they're rectangular, what you give is called a hydraulic diameter. It's like the equivalent of diameter had been a circle. Okay, so you can hear this term hydraulic diameter. It has to do with shapes that are not circular, but it's like a diameter, the term that you're getting. We need to know how to calculate cross-sectional area. So let's take a look at an example of this. So if we wanted to, say we had a circle here, okay, and we knew that, I don't know, this sector of the circle was 120 degrees. And I want to know that cross-sectional area of this sector here, given that the radius is equal to 5 centimeters. I wanted to know that area. How do I figure out area of different parts of the circle? So like, if I had a pipe running through the cross-sectional area, I cut through the pipe, it's just a circle, right? Take a pipe, slice right through it, perpendicular, you're going to get a circle. That's the shape. But if you had a pipe and you cut at an angle, the cross-section is now an ellipse. Think about this pen as the pipe. If I cut directly through it, and I look into the circle, look into the pipe, it's a circle. But if I cut at an angle like this, like anybody ever prune your, well, you ever get roses before, like flowers, and anything like keep flowers good for a long time? You don't cut them perpendicular, how do you cut the stems? At an angle. It increases the cross-sectional area. Because when you cut like this, you now have an ellipse. The elliptical shape allows more water to go into the flower. So that's when you cut a rose, you cut it like this usually when you're going to put it in water. So when you cut something that's not at a right angle on a pipe, you're going to get an ellipse in the cross-section. So we need to be able to figure out random cross-sectional areas. How about this part?
You find the area of the whole circle and then just divide that by a third.
Why?
Because 120 degrees is a third of 3.
So generalize that statement more, Johnny. What if it was 125 degrees, right?
But it would just, you take it as a fraction of the whole area of the circle.
Very good. So again, every time you do this, if you want the area of a sector, it's pi r squared times n over 360, where n is the sector angle. Okay, that's exactly what Johnny just said. He said, you know what, 120 over 360 is 1/3, so he said divide by 3. But if you're giving an arbitrary angle and you need to figure it out, then you can determine that value by plugging in for n. Okay, just your general circle geometry needs to be known for this class. You don't need to know, your laws of secant lines and product of these two equals that. Like, that stuff's never going to come up. But things like the word tangent, we're going to use today, has to be known, like a tangent line, what that means. What do we have, a minute? All right. Yeah. Let's pause there. We're going to start the next. First of all, we're going to take a general look at geometry here in this section, but I want to talk about concentric circles with engineering applications. What is a concentric circle? Or what are concentric circles? Because it needs to be plural. You can never have a concentric circle. It has to be concentric circles. There's more than one circle. So what do you think concentric means? Who knows their Latin and Greek pretty well? Concentric.
In the circle.
Close. Close. It's within the circle, that is right, but there's something more specific about it. Okay, still very close, because it is equidistant, but there's something specific you're missing. Think about a bagel. All right, you get a bagel, and assume a bagel is made perfectly. It's a circle within a circle, which is kind of what Vic said, though, but there's something specific about it. Okay. There's something else. Listen. There's something else that we're all missing. Yeah, it's a circle within a circle, but look, ready? Look. For example, ready? These are not concentric.
It's the center of the circle. Little circles in the center.
They have the same center. Concentric. C-O-N means with. Like they have the same center. They're sharing that. So that is not concentric here. An example of concentric circles would be, and this again is a sketch. Doing my best. Okay, that's a concentric circle. Now, where do you see concentric circles in engineering? You see them all the time. What? A washer. Perfect. This is a washer. You want to put a bolt and a nut to fix together two pieces of metal? You put a washer between it. A washer is really two concentric circles. Concentric circles are everywhere in engineering. Think about pipes. A pipe is a concentric circle. You have an outer wall and you have an inner wall. And the thickness of that wall is really this thickness right here. This is a pipe. That's all it is. Here is the outer diameter or outer radius. Here is the inner radius. Here is the thickness of the wall. Do we all see that, how it works physically? So if you're talking in engineering or just modeling for home, if you want to know that the pipe has a certain wall thickness, you can take the outer diameter, or outer radius rather, and subtract the inner radius. If you use diameter, you have to take the outer diameter minus the inner diameter and divide by 2. Because you get 2 wall thicknesses then, right? Think about it geometrically. Okay, I'll show you another diagram on the right here. If instead you use diameter, take a look. Here's the inner diameter. Here's the, whoops, that's not even close. Can I undo that? Of course I can't. I hate this app. Okay, so this is the inner diameter. This is assuming that we have diameter in this problem, so diameter inner. And the outer diameter would look like this, from here to here. So if you were using outer and inner diameter, if you subtract the outer diameter minus off the inner diameter, you get 2 wall thicknesses worth. You see that? Take, and look up if it helps. Take the outer diameter, subtract the inner diameter, you end up with 2 wall thicknesses. So you'd have to divide that answer by 2 to get the thickness of the wall. But for the radius, if you take the outer and subtract this inner piece, you end up with the wall thickness exactly. Okay, so if you want to, you don't have to write these formulas down because honestly they should be common sense. But if you want to write them for now, Okay, those both work. Either way. The wall thickness is outer radius minus inner, or the wall thickness is outer diameter minus inner divided by 2. Some applications of engineering use radii, some use diameters. That's why I'm giving you both. Okay? Questions so far? Awesome. Now, if there are multiple walls, for example, we have 3 different walls set up. This is used a lot with insulation. So here's a PVC pipe. And here's the inner wall of the PVC pipe. It's very difficult for me to draw a perfect circle, sorry. So assume a perfect please. So that's the PVC pipe. And this PVC pipe is carrying, let's say, hot water in your house. What would you surround it with? Ever look in your house and like the heating duct systems in your house? What do you have? It's like this foam insulation. Very good, Julia. It's a foam. So it's like this layer on the outside that acts as an insulator. This is what I mean by multiple walls. So this is the foam in red. In black is the actual like copper or PVC or whatever the piping material is. If it were hot water, it'd probably be copper actually. It probably wouldn't be PVC. PVC is used a lot for waste pipes. Okay? So we have PVC, we have an insulator on the outside. What's going through the middle of it? Water. This is a cross section. Do you see that? Here's the pipe right here, my pen. I take the pipe and I slice through it with a saw. And then I turn the pipe and then you look at it. Well, what's the shape you're going to get? You're going to get concentric circles. Okay, please don't do this at home because you will ruin your house. But if you cut through a pipe where water isn't running through, you will literally see a circular cross section. If you cut through at an angle through that pipe, you won't see a circle. You'll see ellipse. Think about it. Visualize. Okay, cut through at an angle. We'll see this better when we do CAD work. You'll see this a lot. You'll see an ellipse if you cut through at an angle. But if you cut through perpendicular to the pipe direction, you will get an exact circle. And you'll get concentric circles like this. Now, let's say I wanted to figure out the amount of PVC needed to make this pipe. Well, to do that, I'm going to need to know how much area the PVC makes up, and then I'm going to eventually multiply it by its length to get the volume. And we'll talk more about volume in a little while to see this, but specifically, let's take a look. So let's say I wanted to calculate the area in black. Okay, the area in black. And let's say that I knew 3 things. I knew that the inner diameter, R1, is 2 centimeters. The second diameter is 3 centimeters. And I know that the diameter, or the second radius, I keep saying diameter, radius, the third radius is 4 centimeters. So here's what I'm talking about. I'll show you with a pointer so you can see. From the center, which is here, to the first wall is 2 centimeters. This is 2 centimeters right here. From the center, which is here, to the outer wall of the PVC, which is right here, is 3 centimeters. Again, from here to here is 3 centimeters. Then finally, from here to the outer wall of the insulation is 4 centimeters. So what are these thicknesses? How thick are these then? If this is, ready, 2 centimeters to here, 3 to here, and 4 to here, how thick are each of these walls? 1. Ready? Watch. This is 2, plus another 1 gives me 3 centimeters, plus another 1 gives me 4 centimeters. So the first radius is 2, then a 1 centimeter thickness gets me to 3 centimeters here, then another centimeter of thickness gets me to 4 centimeters out here. So we have, again, if I were to draw this geometrically, that's 2 centimeters, and the thickness is 1 centimeter for both. Okay, for both. If I wanted to find out what the area of the shaded region in black is, okay, I'm manufacturing these PVC pipes. I want to minimize my cost. My goal is to have such thin walls, but it still works without losing structural integrity. So I need to know how much PVC resin I'm going to use to actually make these solid walls. So I need to know the volume, but to know the volume of PVC, I need to know the cross-sectional area. So the question is, find the area of the black shaded region. How do you figure that out? And first I'll give you a hint that there is extraneous information in this problem. There's more information than you need. You don't have to use every piece of info that's given for this problem. How would I figure out the black shaded region? Julia, what do you got? Close. So you have the starting point right. Starting point is absolutely right. A equals pi r squared. If you use pi times 2 squared, that will give you the area of what? The open circle. Good. Not the shaded region. Remember, if I do pi times 2 squared, that will give me the area of where the water passes through the pipe. Okay, there's water flowing through the pipe, and we want to know what the pipe's area is, the black shaded region.
Would you find the area of the red circle and then subtract the area of the small circle?
Very close, Vic. Very close. She's on the right track. Somebody help her out. There was one little mistake.
It's like the entire circle itself minus the small circle.
Which circle?
The
Outer red or outer black? You talking about, Patty, you talking about this one here?
I thought it was
Or this one out here?
outer red, like the entire thing.
That's what she was saying.
Then it's outer black.
Let's think about geometrically, ready? Let me think about it geometrically. If I take the overall circle, right, and I subtract, say, this region right here, I'm going to be left with this entire thing that's shaded plus this. If I take the overall circle, right here, that entire thing, and I subtract this, which is right here, I'm going to be left with this entire area right here, the red and black combined. So this red region is extraneous. We don't need it for this calculation. Take this one right here, think about this circle right here, and subtract this circle right here. What are you left with? You're left with this part right here. Now, it's not 1 numerically because you have to worry about pi. Don't forget about pi. So take the area of the outer pipe wall, not the insulation. Area of the outer pipe wall, assuming this is the entire circle. So we'll say that the area of the shaded region equals the area from the outer wall, which is pi times 3 squared, minus the area of the inner part, which is pi times 2 squared. Again, this is the area of the pipe plus inner, and this is minus the area of the inner part where the water flows. If I want the area of the pipe, which is what I'm trying to figure out, how much material we use for the pipe, I would take the area of the outer pipe, which is this black shaded region, plus the middle area, that's what this is really. That's the overall middle part. Subtract that inner part where the water flows. So take the outer part of the pipe, subtract off where the water flows through. That will give you the area of the black shaded region. Okay, this is really just, remember segment addition postulate from geometry? And there was also something probably called area addition postulate. It's really all it is. You take an outer circle, minus off the inner circle, you get the ring that's left over. How do you get a bagel? Take the outer, think about the overall area of a bagel, subtract the hole in the middle, you get what's left for the bagel. You're trying to figure out the area of the bagel in this problem. Okay? Where the inner hole, where the bagel is, where the hole in the bagel is really where the water is flowing through here. So take the area of this circle, I'm going to highlight it in case you need to do this on your own. Area of this circle here, minus the area of this circle here, will give you the shaded black region. Okay, so that's going to be 9 pi minus 4 pi. How many pi's is that? 9 minus 4? 5 pi's. That's right.
So should we leave it like that, or should we?
I mean, you can multiply by 3.14 and give a number. I don't care either way. Okay, I might make it a multiple choice on your quiz. A question like this, and it might be in terms of pi. Your answers might be like 7 pi, 2 pi, 3 pi, 4 pi. So then you probably wouldn't want to multiply it out.
Do you have to do it like exactly like that? Or can you do like 3 minus 2 because you're only looking for that average?
What's 3 minus 2?
1. Oh.
1 squared is only 1 though, isn't it?
Okay.
See that? Because you're squaring them, Paul. So you can factor out the pi and do pi times the quantity 3 squared minus 2 squared, which will still give you 5. Okay? How would this change? Ready? This is like an easy problem. You should be able to do this. I give you a follow-up in the test. Find the area of the insulation in red now. The area of insulation in red. What would change about the numbers? Don't even give me the whole thing. Just change these numbers and you'll be able to do it like that. I want the red insulation now. Mars.
Would you change this 3 to a 4?
Exactly right, Mars. Let's go through this again. Ready? I want the area of the red shaded region here. The outer radius of the overall thing was 4 centimeters. And if we subtract the inner part right here, so we take the overall circle, which is the outer, minus off this circle right here that I'm highlighting, and we'll get the red shaded region as a result. So if you take the outer wall, the area provided from the outer wall, minus the area provided from the inner wall of the insulation, we would get the area of the insulation. So change this to a 4, change this to a 3, square them both still, so it'd be 16 minus 9 really, and you end up with 7 pi for the area of the red shaded region. Okay, so concentric circles are very, very important in geometry for engineering. Okay? Anything else that I want? No. All right. Tangent lines. First of all, geometry. What is a tangent line? Or pre-calc or whatever you want to answer with. Vic?
I don't know if this is right at all. Is it like a line that's equidistant, or like it is equal to the center, to an outside point of a circle, something like that?
It has to do with a circle and something with the outside. No, you're right. It has to do with the outside, but not the center. It's not the center.
It's perpendicular to the circle.
Perpendicular to what?
The outside of the circle.
Yeah, that's not the right word, perpendicular. I know what you're saying, though. I do know what you mean, so I know what you're saying, but that's not the right word. It touches the circle at exactly one point, making it perpendicular to the radius. So here, if I have a circle, this is a tangent line. Here's the radius, right? There's the perpendicular part, Leslie, that you were thinking about. Okay? So a tangent line is always perpendicular to the radius. But a tangent line touches a circle once. Why am I fussing over tangent lines right now? Because it's engineering, yes, that's part of it. Why am I fussing over tangent lines? Think about life every day around you. Where do you see tangent surfaces and tangent lines? Give me an example, because they're everywhere, so I want to hear from you. Where do you see tangent lines or tangent surfaces? Wheels! Perfect. A wheel on the ground. The wheel is always tangent to the ground. Now, if there's enough weight on the wheel kind of like is flattened a little bit, right? But the wheel itself is tangent. Think about sports. You hit a ball where the ball makes contact on the bat, or the soccer ball makes contact on your foot. There's a point of tangency. How about a pulley system? Isn't that what that is? Isn't that just a pulley that I just drew? Put a little rope on this side now. And now it's a pulley. You lift an object up with a pulley. Well, there's tangency. So points of tangency exist everywhere in engineering. We need to know how tangent lines work. Now, you're going to see as well that in our 3D printing, in our 3D design stuff, that we're going to have a lot of tangent points. We're going to have what are called constraints, where a line needs to be tangent to a surface. So knowing what tangent means is really what's important right now. Okay? Does that make sense? Do you understand what tangent means? Is everybody clear as to what tangent means? And I don't just mean lines, again, I mean surfaces. So as Nora mentioned, a wheel rolling on the ground, the bottom of the wheel that touches the ground is tangent to the surface. Okay, this is now two-dimensional tangency versus, or three-dimensional, I guess. Okay, versus where you just have a line touching a circle. Now it's a surface touching a cylinder. And just to honestly show you what I mean, I don't know why I'm not just showing you. Here's a wheel, right? Okay, this is rolling along the ground. This cylinder has a point of tangency where it touches the ground. That's the point of tangency right there. And then it rolls, the point of tangency changes. But the point of contact of a wheel is its point of tangency, really. Quadrilaterals. We need to know our quadrilaterals in general. We need to know some properties of them. So we start with the most basic of the quadrilaterals, which is simply an amorphous quadrilateral. So anything. Let's see. Okay. That is not a trapezoid. Why is it not a trapezoid? Because I didn't tell you that the sides were what? Parallel. There it is. Not equal. Parallel. Since I didn't say that the sides were parallel, it's not a trapezoid. But if I do this now it's a trapezoid. Okay? A parallelogram has two sets of parallel sides. This is all review from geometry, so I'm going through it quick. If you don't make sense of it, please ask me. A rhombus is a parallelogram, but the sides are also what? equidistant or equilateral, yes. So these sides are all the same length, and you've got sets of parallel sides as well. So again, we've got trapezoid.
Whoa.
Any Star Wars fans? It's a trap. This is a parallelogram here, and this is a rhombus over here. We're also missing a rectangle, which is just like a parallelogram, but instead it's got right angles. Okay, you still have parallel sides, just like a parallelogram, but it's got all right angles. And then the square is the compilation of every shape, or all these shapes' properties. The square has all the properties of all the ones we've listed just now. There's also some other properties like the product of the diagonals equal each other and all this other. I don't care right now. It doesn't matter. Okay? What matters right now is the lengths, the facts that they're parallel, and the angles that they meet at. That's what's important. Okay? You see what I'm saying though? Like the diagonals of a square are equal to one another also, but you could prove that with Pythagorean theorem. You don't need to actually memorize that. You could prove that this diagonal is the same as this diagonal also with Pythagorean theorem. Okay, you do not need to actually write that one down. But know your general rules of quadrilaterals. Polygons. What do you know about the angles of a regular polygon? And I'm talking about angle measurements now. Let's take a look at one of our most powerful shapes, the hexagon, which is used a lot with honeycomb structures, which are becoming more and more prevalent in engineering. Honeycomb structures are used everywhere. A lot of structural integrity, not much material needed. When we do 3D printing this year, I'm going to show you, I'm going to pass this around, this 3D printed object, to show you what I'm talking about. Take a look at the inside of the 3D printed objects. I was 3D printing something and I stopped halfway on purpose. What shapes do you see? Hexagons, polygons, or hexagons. Look, it's the honeycomb structure on the inside. Okay, the honeycomb structure is extremely strong as a break, of course. Okay, this one is not a honeycomb structure. Okay, it's a little bit weaker. The infill changes. Of course, I broke it on the line. Of course that happened. Now, how do I figure out the angles inside of a polygon? How do I figure out the angles inside of a polygon? Anybody remember that formula?
Oh, wait, no. Okay, good.
Vic?
What? Could you find like the area of the two triangles first?
That's a polygon.
You could break up any polygon into pieces to find area, but I'm saying the angle measurements. I'm talking about these holes. How do I know what the angle measurement
Well,
is?
it's 360
Another 360 minus.
divided by.
That gives you the exterior angles, right? Remember, guys, if you want to figure out what this angle is right here, you could take 360 and divide it by 6, because the sum of all exterior angles is equal to 360. But if I want the interior angle, right, so all these angles together are going to add up to 360, which makes each of them 60 for the exterior. But if I want interior, okay, I can subtract that from 180 and just say, well, this is just 120. Right? 120 and 60 gives me 180. But you could use the formula that you learned in geometry. The formula tells you that if you want the measure of an interior angle, you take 180 times n minus 2 all over n. Okay? Remember, if you forget how to do this, think about a triangle. How many sides are in a triangle? 3. What's 3 minus 2 right here?
1.
And isn't the sum of the area of the angles of the angles of a triangle 180? 180 divided by n would be 3. 180 divided by 3 would be 60. So an equilateral triangle is 60, 60, 60. So try this out for a triangle always and check to see that you have the right formula if you forget it. Okay? So, no formula sheets. Okay, no formula sheets. Type it in your calculator at least. Do something. So, let's say it's an octagon, right? Let's say it's an octagon. What would I plug in for n? 8. 8 minus 2 is 6. 6 times 180, all divided by 8, gives me the interior angle of an octagon. Okay, so n is the number of sides or angles. Because it's the same, obviously. This only works for what kind of polygons? What's the term?
Regular.
Regular. Very good. Very good memory, guys. That's a long time ago. It's 2 years. Regular polygons are what it works for. Okay? Let's see. Regular polygons, wasn't it?
Yeah.
Yeah, nice. I didn't realize that. Still, good memory. Let's take a look at 3D solid. So, what's a cylinder, first of all? What's a cylinder?
Rectangle.
It's not like a cone. What is a cylinder?
Rectangle and 2 circles.
So, it's what? Connecting two circles. Guys, ready? A cylinder is the connection of 2 circles. That's all it is. Go ahead and draw a circle. Make it like an ellipse so we can do 3-dimensional. Draw like another ellipse, and then just go like this. And there's your cylinder. Okay, just draw a can. Draw an ellipse, and connect them. I'm looking at this from like a profile, so they look like ellipses, but the ends are really circles. Okay, if I looked at this head on or from the top, it would literally look like that. That's all it would look like. If I was looking down at a cylinder from above, look at a can of soup, what would you see? You would see a circle. That's all you would see from the top. So, we want to talk about the volume for any sort of 3D solid. And I'm going to use a circle to go over the general rule that we're going to utilize here. Okay, I'm going to use a circle specifically to go over the rule that I want to talk about. So if I want to know what the volume of a cylinder is, what I need to do is think about this. Imagine I found the area of this. Okay? Imagine I found the area of that. And then I thought about, like, okay, well, the area of the circle, what if I keep stacking circles on top of myself? You know coasters? Coasters, like circular coasters? If you stacked coasters, what would they make? A cylinder, wouldn't they? So isn't it really just like a bunch of areas of coasters stacked up by a certain amount of height? Yeah. So what we can do is we can generalize. We could say that the volume of any prism is equal to the area of the base stacked up, or times the height. That is the volume of any prism, assuming, obviously, that the ends of the prism are the same. A cone, you cannot use this formula for. A cone is tapered, right? Or like a fire hose, what a firefighter uses, it's got a big end of one nozzle, a small end here, so that the flow of the water increases so it can reach the heights that it needs to in the building. We did that example in physics last year. A baseball bat is not a prism. A baseball bat is a giant barrel and a tapered handle that you hold on to. It's not a prism. A prism has the same cross-section throughout. Okay, so this, believe it or not, would be a prism if you consider this the base and you consider this the height now. This is a triangle. It's a triangular prism. That's all it is. This base is the same as this base, and you've connected them. That's what a cylinder is. You take any 2 objects that are the same and connect them. This is a prism right here, generally speaking, without these things. Here's one base, here's the other base, and you've connected them. So if you found the area of this base right here and multiplied it by the height, you would get the volume of this object. This would be a great example. This is one base here. This is the other base here. This, it's kind of contoured, so it might not be a perfect prism. But the idea of it being a prism. Okay, so a lot of things can be modeled as prisms. Like here is the rule of thumb. So that's where the formula comes in for this. So let's take that idea, okay, and look at a rectangular solid. Draw a rectangle. Draw 3 lines back like that. Connect the top 2 lines. Connect the side 2, and you got yourself a little prism. It's obviously not phenomenal, but do your best. You can connect with dashed lines to show the depth of the prism if you'd like to also, so you can physically see it. Now, what formula have you always been told for the volume of this? What's the formula always that you use? Length times width times height. But length times width is really the area of the base times the height. Again, this is really LW here. This is the length, this is the width, and this is the height. So the area of this front base right here is LW times the height. So this is for a rectangular solid, the specific formula. And again, it's the area of the base area is LW, that's the area of this, times the projected height. Project means the 3rd dimension. What would the volume of a cylinder be? What's the area of the base of a cylinder? Circle. What's the area of a circle? That's the area of the base times the height. Okay, so there's the volume of a cylinder. So I could give you any shape as long as you know the area of the base. You just have to multiply it by the height and you get the actual prism's volume. Very useful for CAD, because in CAD we take 2-dimensional things and what do? We extrude them or project them. Okay, we extrude or project those values. Let's see. 3D solids are everywhere, obviously. I don't even need to go into detail, but think about anything. Think about a screw, a pin, a bolt, a fin. What's a fin? A fin is like those little flaps on an air conditioner. The coils of the radiator right there. That radiator, believe it or not, those fins that are projected outward are three-dimensional objects. So we're looking at prismatic shapes throughout this section. All right, let's stop with 3D for that. I want to take a look at two types of symmetry. In geometry, you talked about rotations and reflections. Did you talk about dilations? What's a reflection? Let's start with the easy one.
It's flipped over the X or Y axis.
Yeah, it's flipped over the X or Y axis. So, if I had this shape over here, and I wanted to reflect it over the Y axis, it would look like this. Sorry, the X axis, it would look like this. Okay, that's the reflection over the X-axis. The reflection over the Y-axis would look like this. Okay, that's all reflections are. We know those right now. How about rotations? How do rotations work? You rotate it. But how do you have rotations with coordinate planes?
Is it like ending is 360, so it's like a circle?
Exactly. It's the idea that a full circle is 360. So rotations work as a function of angles. So if I tell you that it's a rotation of 90 degrees, it means that the object goes from here and you rotate it 90 degrees. If it's a rotation of 180, is that the same thing as a flip over the horizontal? Think about rotating 180, same thing as the flipping over the horizontal. This is extremely useful in the next section of CAD, because you know what? What if you want to design something that has many objects, or many like holes in it, or pins? Do you want to sit there and design each pin individually? No. You want to put what's called an axis. You're going to put an axis in CAD, and you're going to reflect it over the axis, and then reflect that over the next axis. And then you might rotate them to have 360 rotation, so you have 4 of the pins. So it saves you a ton of time. So knowing your rotations and reflections are important. Now how about this one? This is the trickiest one of all. And it's hard to see because it's three-dimensional. What if I had, let's say I want to make like, what's an easy shape? A vase. A vase. Okay? I know. Weird. But a vase. Anybody ever make a vase before? What is that called? What's the term? Pottery. Okay. So say you want to make I just couldn't remember what pottery. With a pottery wheel, doesn't it spin? And don't you like curve it with your hand and all this stuff, right? So there's rotational symmetry involved in pottery. So watch. What if you do this? What if I have some sort of a shape like the following? Let's say the shape is this. Okay? And what if I rotate this shape around the y-axis? I take this shape, I should make that a little bit better.
Which way do the rotations go? They always go this way?
They always go clockwise. Well, now I shouldn't say that. It really depends. It really depends. It really depends. Because in math, you're going to learn that you started the terminal side this year, but you learned last year. Actually, that was too trick. And you learned that you rotated this way, right?
Yeah.
That's counterclockwise. In engineering, you have to clock. It really depends on the application. So let's say, take a look, please. Let's say this rotated about the y-axis like this. Okay, rotate this around the y-axis. The shape that you would get from rotating around the y-axis would be a bowl shape. Okay, you would get like a bowl shape. Think about it. You would have this little V in the middle. It would be like a cone that's emptied out. Imagine like in soccer. You know the cones in soccer? Regular cones turn upside down. This shape in the middle would have that, but you have like a curvature on the bottom. You know the soccer ones that are like kind of, the ones that are like curled and hold? You know the ones that we use, the small cones I'm talking about. Not the ones with the top on them. So if you rotate this around, you'll get this kind of a shape. Take a look. Okay, and this shape will continue its way throughout the process here. It will look like this, and it will come up to the wall. I know it's ugly as anything. Okay, but take a two-dimensional shape. Listen. Take a 2D shape and rotate it. You'll get a three-dimensional solid. Let's go with an easier one. Very easy one. I'm sorry, that was too difficult for a shape. Let's say we have A rectangle.
No, that's the same shit.
Let's say we have a rectangle and we want to rotate it around the y-axis. That will give me a shell of a cylinder. Think about it for a second. Okay, I'm going to sweep. It's hard to demonstrate this. Ready? Watch the rectangle. Here's the vertical axis. Here's the vertical axis. Ready? Right here. Here's the rectangle. Revolve. Guys, focus. Stop. Focus. You need to look up. I'm showing you, so you need to look up. Here's the vertical axis. Here's the rectangle. Revolve it around the vertical axis. What you would end up with would be a shell, like literally a shell, the barrel of a gun. Think about the barrel of a gun. You cut off the end of a barrel. It's a cylinder. That's all it is. Revolve this around it, you get a three-dimensional solid. In CAD work, you're going to do a ton of revolving and extruding. So you might have a rectangle, and you might extrude it to the third dimension, and then you get a prism. But if you take a rectangle and revolve it, you get a cylinder shell. So we're going to see a lot of this with CAD work. So it's important that we know that when we do something like this, we have to rotate it around it, and we end up getting a cylindrical shape. Okay, we'd end up getting a cylindrical shape, however long this rectangle goes. Maybe it goes down to here. Okay? All right. All right, so let's take a look at some right triangles. Let's take a look at some right triangles. We only have like 2 things left. That's it. Okay, we already did all the Excel stuff, which are all the other slides later on. So how do you find the area of any triangle? Here's your formula. In math, we use K a lot of the time for area for here. I don't know why, but I'll use A for the sake of this. A equals 1/2 AB sine C. Now, I know, it's something that's new. Something that's new for sure. And you're going to learn about it this year in pre-calc class. Okay, 1/2 AB sine C. Where A and B, then you'll learn it right now. Then A and B are the legs. C is the angle between them. Write this down, please. If A and B are 2 given legs, C is always the angle between them. So if I give you a triangle, it does not have to be a right triangle. That's the cool part. A right triangle, yes, you could use 1/2 base times height. That's fine, or if you knew the height. But say you knew that this was 20 degrees, this was 40 degrees, it's going to be 60, which makes this 120 degrees. Okay, and let's say I gave you a length of 4 and 7. James, which angle am I going to use then, if this is the problem here?
Yeah.
How am I going to do this? Which angle am I going to use?
120.
Good. Why? Explain to the class.
It's between 4 and 7.
Yeah, so remember A and B are the side legs? If A and B are the side legs here, and C, just focus please. If C is this length, it makes this angle C, right? Think back to geometry. If this is A, if 4 is A, then 40 is capital A. If 7 is little b, then 20 is capital B. Okay? If this is little c, then this is capital C. So whenever you want the area of any triangle, you do 1/2 times one leg times the other leg times the sine of the angle contained by those legs. That will always, 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 always give you the area of the triangle. For any triangle, you don't need 1/2 base times height anymore. Okay, you can always use this formula here. 1/2 base times height comes from this, because it's a 90-degree angle and the sine of 90 is 1. So if you have a right triangle, this just drops off right here, and you end up with 1/2 base times height. That's where it really comes from. But the formula that you need to use, again, the formula that you need to use here is 1/2 AB times sine C, where C is the angle contained. Pythagorean theorem, we all know, equals what? What's the Pythagorean theorem? Okay, thank you. So leg squared plus leg squared equals hypotenuse squared. Be able to find any leg given the other 2. Again, geometry. Basic math stuff, but you need to recall that information. So remember that A and B are always going to be the legs, and C is always going to be the hypotenuse. So for example, if I want this leg, and this is equal to 10, and this is equal to 7, figure out what B's length is, we can plug into the formula. We could say 7 squared plus B squared equals 10 squared. 10 squared is 100, 7 squared is 49. 100 minus 49 is going to give me 51. Okay, I'll show the work in case anyone's confused. Subtract 49. So b is equal to the square root of 51. Okay, the last thing, real quick, give me another like 10 seconds. The last trig functions. Okay? Be able to work with these to find the side lengths. Tomorrow, we'll make sure to review anything we missed. But you're going to have a quiz on the math stuff on Thursday. Get ready for Thursday quiz. And then Excel will be on Monday. Tomorrow, a mouse and a flash drive, please.